Okay, so by now, I guess the word has gotten out that this is all we do all day long in first period.
I wish I wasn't so dang sweet, so dang sweet, so dang sweet. I wish I wasn't so dang sweet. You are like cinnamon. Hey guys, what you doing? Avoiding death? Come again? I'm avoiding death.
And I'm really freaking thinking somebody's gonna shoot me.
You'll be good, bro.
I just wanna see a tree.
And you will.
No, I won't.
Shaggy won't be at the barbecue. Then again, I guess he is a barbecue.
Well, that's not what we do all the time. Anyway, this video kind of picks up where the last one left off. And the last thing I was talking about in the previous video was the second law of thermodynamics, which gives us the actual criterion for spontaneity in reactions. And that is that any process that is spontaneous is going to be spontaneous because it is causing the entropy of the universe to increase. And therefore, any process that we can for which we can determine that we're causing the entropy of the universe to decrease will be non-spontaneous, and that would not occur without outside intervention. So in other words, as I said before, for spontaneous processes, delta S of the universe, and remember, universe equals system plus surrounding. For a spontaneous process, it's greater than 0. For a non-spontaneous process, it is less than 0. And for an equilibrium process, and I mentioned again, this is going to come later in the year, then delta S of the universe would actually be equal to 0. Okay, now, this is just one other thing I thought I'd throw in here to brighten your day. As a result of all spontaneous processes, the entropy of the universe increases. And in fact, there really is no such thing as a non-spontaneous process. The things that we do in the world to bring more order and to reduce the entropy of the system are actually done at the expense of energy coming from the sun or something. And it's always the case that ultimately every process on Earth is a spontaneous process because if it is not spontaneous itself, it is being driven by energy from some other spontaneous process. So in other words, since everything that occurs is ultimately spontaneous, the universe is slowly winding down, and one day the lights are going to go out on all of us, but probably not in our lifetime. Okay, so because we have this law that delta S of the universe is positive for any spontaneous process, we can construct a table like this, in which we just basically say, remember, the universe is made up of the system plus the surrounding. And therefore, if the delta S of the system and the delta S of the surroundings are both positive, then delta S of the universe must be positive, and that is always going to be a spontaneous process. For a process in which the delta S of the system is negative and the delta S of the surroundings is negative, then of course that's going to cause delta S of the universe to be negative, and that's never going to be spontaneous. If it's negative for the system but positive for the surroundings, then it's going to depend on the magnitude of these two figures. And if it's positive for the system but negative for the surroundings, then again, it's going to depend on the magnitude of these two numbers, whether or not the process itself is spontaneous. But the question arises, and we have ways of fairly easily determining delta S for the system, and I'll talk about that in just a few minutes. What actually is it about a chemical reaction that's going to cause the entropy of the surroundings to increase? Because that's something that we want to have happen in order for something. That's going to tend to favor spontaneity, to have the entropy of the surroundings increase. What is it about a chemical reaction that's going to make the entropy of the surroundings increase? Well, if you go back to this equation I gave you yesterday or in the last video, the entropy change of the surroundings is equal to the Q of the negative Q of the system over the temperature. And since we're typically talking about things happening at constant pressure, the delta S of the surroundings is negative delta H over T. So let's think about what happens if this is exothermic. If it's an exothermic process, that means that the delta H of the system is negative. A negative is going to give us a positive, and therefore the entropy of the surroundings is going to go up. And you can just think about this sort of just in terms of if delta H is negative, that's an exothermic reaction. It is transferring heat to the surroundings. That is going to add kinetic energy to the surroundings. That is going to give more microstates to the surroundings. That's going to increase the entropy of the surroundings. And therefore, any exothermic reaction is always going to increase the entropy of the surroundings. And this is why exothermic reactions tend to be spontaneous, because an exothermic reaction is a favorable thing in terms of spontaneity. It's not the only thing, but it is a favorable thing to have an exothermic reaction. Okay, let's think about qualitatively predicting the sign of delta S of the system for a chemical reaction. In other words, can we look at a chemical reaction and not make a quantitative calculation of delta S, but simply ask ourselves, is delta S of the system going to be going up or is it going to be going down? Well, as we said in the last video, in general, the entropy of the system is going to increase if I have a reaction that forms gases from liquids or solids, if I have a reaction that forms liquids or solutions from solids, if I have a reaction in which the number of gas molecules increases, or a reaction in which the total number of moles of substance increases. And so let's take a look at some reactions. And so here's an example, and this is from the test bank for chapter 19 of your textbook. Let's take a look at this question. Delta S is positive for which of the 5 reactions below? Let's put those principles that we were just looking at into practice here. Well, in A, I'm going from gas to gas, but I am going from 3 moles of gas on the reactant side to 2 moles of gas on the product side. That is probably not an increase in delta S because I'm decreasing the number of moles overall in the reaction, and I'm decreasing the number of gas moles in the reaction. 2 NO2 combining to give me 1 N2O4. Same thing. I'm going from 2 moles of gas to 1 mole of gas. That's going to result in a decrease in delta S. In deposition, which is the opposite of sublimation, in which we go directly from gas to solid, that clearly is going to reduce the entropy of the system, going from a gaseous state to a solid state. Dissolving in barium fluoride to give me aqueous barium ions and aqueous fluoride ions. This is probably going to increase the entropy of the system. We've talked about in the last video the fact that dissolving things doesn't always increase the entropy of the system, but let's just assume for the second that D is in the running, and let's look at E. Well, here I'm going from a liquid plus a gas to a solid. That's bad. And I'm going from 3 moles of reactants to 2 moles of products. That's bad. And therefore, that leaves us D as the only possible answer. This is the one for which delta S is positive because I'm going from a solid to a solution. Okay. We can do better than just qualitative predictions of delta S. We can actually calculate them quantitatively because in your textbook we have tabulated data for entropy of substances. How do we get them? Well, we get them from what's called the third law of thermodynamics. And the third law of thermodynamics says that if I have a pure substance and I have it in its pure crystalline form, then at absolute zero, that is 0 Kelvin or negative 273 degrees Celsius, it has an entropy of 0. And that makes sense because at 0 kelvins, it has no kinetic energy. Therefore, it's not moving at all. Therefore, it only has 1 microstate. And actually, entropy is a logarithmic function. And so the log of 1 is 0. So I've got no entropy with no temperature. As temperature increases in the solid phase, entropy increases because now I've got vibrational kinetic energy. Then I go through a phase change to go to a liquid. That increases the entropy quite a bit. As I continue to heat that liquid, again, it gets warmer, more microstates, more entropy. I boil that liquid. Now I'm going to the gaseous phase where there's a lot more entropy. And then as I heat that gas, the entropy of that substance is going up again. It turns out that people that are into physical chemistry and are much more intelligent than I am in this regard can actually calculate the entropy, the absolute entropy of a pure substance anywhere along this curve. And those are called standard enthalpy. Those are called standard entropies, and they are tabulated in your book. So the third law allows us to determine the absolute entropy of any substance under any conditions, but it's tabulated in your textbook under standard conditions, which is 25 degrees Celsius, 1 atmosphere, and for solutions, a concentration of 1 molar. And so here's table 19.1 from your textbook. It's a list of standard molar entropies for a few selected substances. Appendix C, you may have already noticed that Appendix C doesn't just have standard enthalpies of formation. It has 3 columns for each substance, and one of those is the standard entropy. And so they've pulled standard entropies for a set of maybe 20 compounds here. And you can see, once again, you'll see the trend that we talked about. In general, entropy is much lower for a solid than it is for a liquid, and it's lower for a liquid than it is for a gas. Now, and we know that for a given substance that's true. For a given pure substance, its standard entropy per mole in the gaseous phase is going to be greater than its standard entropy per mole in the liquid phase, and that's going to be greater than its standard entropy per mole in the solid phase. But another question arises from that table that we just looked at, which is, why are the standard entropies of some compounds greater than others in the same state? In other words, if I've got a group of gases, why is it that they don't all have the same entropy? Why is it that some compounds have a greater entropy than others at the same temperature in the same state? And the answer to that is that larger and more complex molecules have greater entropies. And that's because the larger or more complex a molecule is, the more, I put here things it can do, but you can think about back to when we were talking about all the various modes of motion of water in the last video. It can vibrate, it can rotate, it can translate, and the more atoms you have and the more bonds you have, the more it can do those things. Thus, you have more microstates available, therefore you have greater entropy. And so here's an example from your textbook of 3 hydrocarbons, methane, ethane, and propane. And what you can see is that particularly when it comes to rotational microstates, you can rotate around these single bonds. And these single bonds, there's only 4 of them in methane. There are 7 single bonds in ethane, and there are 10 single bonds in propane. So you've got a lot more rotational microstates, and you can see that the entropy is going up from methane to ethane to propane. Now when you go back and look at the table, what you'll see is as mass goes up, nitrogen has a higher standard entropy than hydrogen because it weighs more. Oxygen has a higher standard entropy than nitrogen because it weighs more. Water weighs less, so oxygen weighs 32, water weighs 18, but it's almost got the same standard entropy of oxygen. That's because water is a more complex molecule. It's got 3 atoms instead of 2. It's got 2 bonds instead of 1. There are a lot more things it can do. And ammonia, although it actually weighs less than water, has 4 atoms in it, has 3 bonds, and that gives it even more microstates and actually puts it up over nitrogen gas. And then as you get more complex gases, they've got more rotational degrees of freedom. They've got greater entropy value because more microstates. Similarly, within the liquid phase, the larger and more complex it is, the greater the entropy. Within the solid phase, the larger, the more massive, the more complex it is, the greater the standard entropy. Okay, so let's do another problem. Of the following, the entropy of what is the largest? So let's just take a look at what we have here. It's giving water in 3 different states, solid, liquid, and gas, and it's giving hydrogen sulfide in 2 states, liquid and gas. Well, we know that for any substance, as long as you're talking about the same substance in every state, the gaseous state is going to be the highest entropy, and so we can get rid of A and B, And we can get rid of E because that's just the liquid version of hydrogen sulfide in the gaseous form. So now it's just down to choosing between answer C and answer D. Well, we just said that entropy increases with size and complexity, and hydrogen sulfide is larger and more massive than water, and therefore the answer to this question is going to be hydrogen sulfide. We said in the last video that entropy is a state function, and therefore we can calculate the entropy change of a reaction the same way we calculate the enthalpy change of a reaction, simply by summing the standard entropies of products multiplied by their coefficients in the balanced equation, and subtracting the summed entropies of the reactants multiplied by their coefficients in the balanced equation. So we can finish off by doing one more problem. This is kind of a complex looking problem, but it's not that difficult to do. This is just a table of data that I pulled out of a test bank, and it gives you standard enthalpies, free energy, which is something you haven't talked about yet, and standard entropies for a bunch of different compounds here. By the way, one thing I just want to point out, it is true that by definition, because this is a delta, we can simply define elements in their standard state as having a standard enthalpy of formation of 0. That's not true with entropy, because this is at 25 degrees, not 0 Kelvin. Hydrogen does have a positive entropy, and it's given here. But if we're looking at the question is, what is the value of delta S for this reaction? C2H2 plus H2 gives C2H4. What is the value of delta S going to be for that reaction? Well, we're simply going to sum up the products, and there's only one product, which is the C2H4. That's 219.4. Its coefficient is 1, minus the sum of the two reactants. Their coefficients are both also 1. So it's 200.8 for the C2H2, 130.6 for the H2. That is my equation. I resolve that, and I get a negative 112 joules per Kelvin per mole. So that's the end of the video presentation as far as entropy is concerned. This will be with obviously an assignment for a QOD tomorrow, and I will post some suggested end of chapter problems with that. In the meanwhile, please enjoy this.
20 nights in the ice is a long time when there's hostiles on the hill. It's not about what they want, you just gotta walk your walk. 20 nights in the ice is a long time when there's hostiles on the hill. It's not about what you wear, it's all about where you are.
Yeah, see if you can give it more bass. Hey, where's the music? Dak is dead.
I wish I wasn't so dang sweet, so dang sweet, so dang sweet. It's not about what they want, you just gotta walk your walk. I wish I wasn't so dang sweet, so dang sweet, so dang sweet. It's not about what you want, it's all about
Dak?
what you want.
Hey guys, I think Dak is a zombie.
Really, what do you mean?
I mean, he's a freaking zombie.
But wait, didn't your ship just get shot?
Yes, but zombie.
It is terrible.
Yeah, you think?
You are like cinnamon.